Hi guys, it's Miss B. Today, let's look at the nature of gases. In the last unit, we looked at solids, whose particles are really packed tightly together, liquids, whose particles are more spread apart, and gases, who don't have a definite shape or volume because their particles are so spread so far apart. This can all be explained by the kinetic theory of matter. This says that all matter is made up of small particles. These are usually atoms or molecules. These particles are in constant motion, and the average kinetic energy of these particles is a measure of their temperature. The potential energy of the particles is going to relate to whether or not it's a solid, liquid, or gas. Now let's look at how kinetic molecular theory relates to gases. First, a gas is made up of particles, usually molecules or atoms. The particles in a gas move rapidly in constant, rapid, random motion. They travel in straight line paths and move independently of one another. All the collisions between the gas particles are considered to be completely elastic, which means the total kinetic energy is constant. We're going to assume they have no volume, and we're going to assume they have no attraction to each other. This is known as an ideal gas. Let's look at a couple properties of gases. First, there's pressure. Solids, liquids, and gases all can be described by volume, mass, and temperature. But gases, we also talk about being affected by pressure. Pressure is the force that's exerted by the collisions of the gas molecules on their container. It's measured by a barometer. You can check your reference table to see the units and the conversion factors: kilopascals, atmospheres, millimeters mercury, and torr. We can use dimensional analysis to convert from one pressure unit to another. So let's take an example. Let's take a look at a couple examples. Standard pressure is 1 atmosphere, or 101.3 kilopascals, or 760 torr. So, how many torrs are in 2.3 atmospheres? What we're going to do is we're going to write what we know, which is 2.30 atmospheres, set up our little conversion factor, and we want to put atmosphere in the denominator. We're going to put 760 torr in the numerator. This allows us to cancel out atmospheres, leaving us with torr. We do the multiplication, we get that that's 1750 torr. Okay, here's the second one. Convert 50 kilopascals to atmospheres. In this respect, we just write what we know, 50 kilopascals. This time, we want kilopascals in the denominator, which is 101.3 kilopascals, and 1 atmosphere in the numerator. This allows us to cancel out the kilopascals. So now when we divide 50 by 101.3, we get 0.494 atmospheres. Temperature is another conversion factor you'll have to deal with gases. When dealing with gases, we have to use the Kelvin temperature because there are no negative numbers. But put this in your notebook, it must be Kelvin in gases. Kelvin equals Celsius plus 273. Note, absolute zero is 0 degrees Kelvin. And this is theoretically the coldest possible temperature. This is also the temperature which theoretically gas particles would cease to move. In fact, all particles would stop moving. Now, of course, that's in theory. So here's an example. Convert 23 degrees Celsius to Kelvin. All we do is we add 23 to 273, getting 300 Kelvin. Please practice these conversions of both pressure and temperature so that when we do a little more math using these values, that you'll be comfortable. And remember, you can get these on your reference table. Notice that here where we get our pressure conversion factors, and using the part on temperature, you can see the relationship about Kelvin.